Hello everyone, thank you for coming to my talk. My name is Aziz Tokyaz and I'm from University of Cambridge. I'm a third year PhD student. And today I'm going to be talking about the fracture behavior and microstructure mechanics relationship of aortic aneurysms. Now, to begin with, I would like to start by giving some information about the aorta. Aorta is the main artery, is actually the largest artery that carries the blood from your heart to the other arteries. And because it's the first artery that the blood faces as it leaves the heart, the aorta has to sustain a lot of high amounts of pressure. And to be able to do this, the healthy aortic wall, where in this picture is this red segment, is made up of 3 layers that are stick to one another like a composite family that we saw in the previous presentation. And each one of those layers have their own fiber structures, and they may run in different orientations in each layer as well. And these layers come together to form the aortic wall and help the aorta sustain these large amounts of pressure of the blood, and then help the aorta distribute the blood to the branching arteries. Now, what are aortic aneurysms? Aortic aneurysms are a kind of vascular disease, and they claim millions of lives every year like every other cardiovascular disease. What they cause is they cause the dilations, in other sorts, local dilations of the aorta, which are called dilatations. And these dilatations are accompanied with fat deposits that infiltrate the aortic wall, infiltrate all of the aortic wall layers, all 3 of them. And they eventually weaken the aortic structure by either causing some voids or causing the original distribution orientations of the fibers to change. And then eventually the aortic wall ruptures, and this leads to fatal clinical events. Now, the main goal of our study is to understand the microstructure mechanics relationship of the aorta. And to be able to do this, we first had to find a surgeon collaborator who provided us with 8 patients that donated their aortic aneurysm pieces. You can see a ring piece aortic aneurysm here, which is cut during surgery, the grafting surgery, where they replaced the aneurysm-affected artery with some plastic graft. And they give us the disease section. And to be able to do the tests, we have to obtain these tensile testing, uniaxial testing strips. And we went on to investigate the mechanical properties of each layer separately. These are the 3 arterial layers that I was talking about. The intima, which is the innermost layer, the media, which is the middle layer, and the adventitia, which is the outermost layer. So we get these aortic aneurysm rings, we cut them up into sheets, and then we separate those sheets into the intima, media, and adventitia layers. And then we cut away strips from adventitia, media, and intima layers. And because we already know that the aortic wall has an anisotropic material property, it will have different mechanical properties in its axial and circumferential orientations. So we obtain these strips both in the axial and the circumferential orientations. We did uniaxial tensile tests on these arterial tissue strips, and we did both unnotched tests to study the conventional mechanical property, and we also did a notch test. We used a surgical scissor to put a notch at the side of the arterial tissue strips during testing, and this allowed us to see how the arterial tissue would behave in the presence of a structural defect. You can see at the bottom of this slide the breakdown of our tissue strips. We did 48 unnotched strip tests and 48 notched strip tests, and 25 of each of those were in the axial and the other 24 in the circumferential, and 8 were intima, 8 media, and 8 adventitia in each axial and circumferential orientation. So in total we had 92 tissue strips. Because we want to know the relationship between microstructure and mechanical properties, we had to look into the microstructure, and to be able to do that, we did histological processing. Now, histological processing allows us to stain for different components in the arterial microstructure, and you can see here that this particular stain, serious red stains for collagen fibers, which are known to be the main mechanical contributors of material strength in arteries, and EVG stain allows us to see the elastin, which is another main mechanical player in the arterial wall. And we also look at glycosaminoglycans, which are in short called GAGs. And the GAGs haven't been really studied in the field of aortic biomechanics. And this is one of the first few works that look directly into the role of GAGs in the mechanical properties of aortic aneurysms. We also had a look at the macrophage cell content, where macrophage cell content is a direct indicator of inflammation, therefore the extent of the disease progression within the aortic tissues. One more piece of information is that we obtained these tissue strips right next to the tested tissue strips, so we were able to assume that the microstructure of these strips were identical to the ones that were tested. The first set of results that we obtained from histological processing was the layer-specific component content, so how much of each microstructural component did exist in each of the arterial layers. You can see the lighter colored one is the intima, and the slightly darker is media, and the darkest one is the adventitia. And when we look at the collagen content, we see that the adventitia has the largest amount of collagen, much larger than both intima and media. And we see that the content of the collagen in the media is still larger than the intima. We didn't really obtain a lot of significant differences amongst the elastic content of these layers. But when we look into the GAG content, we saw that although the content of GAG is same in the intima and the media layers, their GAG content was much larger overall than the adventitia layer. I want to stress at this point that we hypothesized initially that GAGs are a bad contributor of mechanical properties. So with disease, we hypothesized that the GAG content will increase and it will cause the mechanical properties to decrease. We also didn't see too much of a difference amongst the macrophage content except for a larger macrophage in the adventitia compared to the intima. When we look at the layer-specific mechanical properties of the unnotched tissue strips, we saw that the circumferential adventitia was the strongest compared to both axial and circumferential intimas and medias. And we also saw that the circumferential orientations of the media and adventitia layers were stronger than their axials. When we look at the extreme extensibility, we saw that the adventitia was more extensible than the media in the circumferential direction, whereas we didn't really observe any other difference between the extreme extensibility of layers in either direction. When we looked at the notched tissue strips, we found out that in the presence of a structural defect, the nominal strength of the adventitia was much larger than the nominal strengths of media and intima in both directions. Another point that sticks out here is that in the case of aortic aneurysms, the disease actually starts from inside of the artery, so from the intima. You can here, the intima is the innermost layer, media is the middle layer, and adventitia is the outermost layer. So this actually gave us an idea about why the adventitia remained strong in the presence of a structural defect with the notched tissue strips. This is mainly because we also saw in the preparation of the tissue samples that adventitia was largely untouched by disease, where the intima and media layers were highly affected and infiltrated with lipid deposits. And the fiber microstructures seem to be disturbed a lot compared to the adventitia. We also saw that the axial adventitia was more extensible than both axial intima and media, and this was the only significant result from the extreme extensibility component. Now, when we come to the main focus of our study, which is the relationship between mechanical properties and the microstructural constituents, for the unnotched tissue strips, we found a positive correlation between the elastin content and extreme extensibility. And this was found to be significant in both axial and circumferential orientations of the tissue strips. Now, in this analysis, I would like to stress that data from intima, media, and adventitia are all pooled together, so I will not be talking about the individual correlations of intima media and adventitia. In addition to the positive correlation between extreme extensibility and elastin content, we found out that the ultimate material strength was also positively correlated with the collagen content. This was actually already hinted from previous studies that collagen would have a relationship with the ultimate material strength, as it is known to be the main mechanical contributor of the arterial wall. However, for the first time in the field of arterial biomechanics, we were able to find a direct link between gap content and ultimate material strength, and for the first time we also confirmed that by multivariate regression. So we plotted the ultimate material strength against collagen and GAG in a 3D plot, and we found out in the multivariate regression that the correlation still was significant. So while collagen was increasing the material strength, GAGs were decreasing the material strength, and their combined effect was still significant. In the case of notch tissue strips, we still found that the ultimate material strength positively correlated with collagen, which was not of a surprise, and this was significant in axial and circumferential orientations. But again, surprisingly, for the first time we found that GAGs played an important role in arterial biomechanics, and they had a negative correlation, as we hypothesized, on the ultimate material strength. They decreased the ultimate material strength of both axial and circumferential tissue strips. And this was, again, the relationship between collagen and GAGs for both axial and circumferential orientations was confirmed with multivariate regression. So after finding all of these interesting results between collagen and GAG content and mechanical properties, we wanted to look at the underlying reason behind it. So what could be that the GAGs are doing and making the material properties worse? And what could be the effect of GAGs on collagen? Because we know that collagen, if the collagen content is still there, they should be able to somehow overcome the bad effect that's coming from GAGs. But what are the GAGs doing in the microstructure that's causing the microstructure property to decrease when there is still collagen? For this, we first segmented the collagen fiber pixels in the tissue, and then we segmented the GAG pixels in the tissue, and we first found the collagen and GAG contents in both by doing support vector machine learning classification. And then we skeletonized the collagen fibers and reduced them to single line pixels, and this allowed us to obtain the orientation of the collagen fibers. After we obtained the orientation of the collagen fibers, we had to look at the relationship between the GAG percentage and the dispersion of collagen fibers. Now, the dispersion of collagen fibers simply implies the distribution of collagen fibers. So the larger the dispersion, the more randomly distributed the collagen fibers are. And you can imagine that the more randomly distributed the collagen fibers are, the less strong you would expect the material to be. So in the case of intima, we didn't have any correlation, but for media and adventitia, in both circumferential and axial orientation, the GAGs caused an increase in dispersion, and these were found to be significant correlations between dispersion and GAG content. Therefore, the GAGs seem to be playing a role in distributing the orientation of collagen fibers and making the structure weaker. Now, in conclusion, along with collagen fibers, we found that GAGs also play an important role in arterial biomechanics, and we found that GAGs could be decreasing the material strength by randomizing the orientations of collagen fibers, and this is indicated by the results from the media and adventitia layers. I would like to thank you all for